Welcome back in our channel. Today we have the second order constant coefficient homogeneous linear second order differential equations. Constant coefficient means here there is no function of x, just constants here and here and here. If there is a constant here, we divide the equation by this constant to get the second derivative by itself. So there is no function of x multiplied by either one of the terms, either the second derivative or first or the y itself. Homogeneous means the right side of the equation equals 0, or there is no function of x by itself or a constant in the equation, either in the left side or in the right side. Because even if it is in the left side, we move it to the right side, and then this side won't be 0. So homogeneous means there is no constant in the equation or function of x by itself, which means the other side of the equation, the right hand side is 0. How to solve this second order constant coefficient homogeneous linear differential equation? If you remember in the first video of our series, we talk about linear and non-linear, which means there is no power in either one of the terms, like y or the derivative or the second derivative. Then there's no multiplication of y and the derivative. No special functions. This was in the first video. The solution. There is an algebraic equation called characteristic equation, in which we replace the second derivative by lambda squared, the first by lambda, and y by lambda to the power 0, which is equal 1. So our differential equation becomes lambda squared plus a1 lambda plus a naught, because lambda to the power 0 equal 1. Then we find the roots of the equation 2 here. To get the general solution of equation 1, there are 3 possibilities for the roots of equation 2. 3 cases. The first one, the roots are real and distinct roots. They are not equal, but they are real numbers. And here, for example, this one, this differential equation, this is the characteristic equation, and here we factor this equation. So we got lambda 1 equal minus 1, and lambda 2 equal 2. So they are not equal, but they are real numbers. The general solution is, this is y1 and this is y2. So the general solution, of course, this is y of x, and y1 of x, y2 of x, okay? So here, this is our solution. This is the general solution. Another example, this is the same. We use double prime as the second derivative. Plus 3y prime minus 10y equals 0. So here the characteristic equation, and here are the roots. Lambda 1 equal minus 5, and lambda 2 equal 2. The general solution is y equals c1 e to the power lambda 1x plus c2 e to the power lambda 2x. And here is our solution. Y equal c1 e to the minus 5x plus c2 e to the power 2x. A special case when they are equal but opposite in sign. Then the general solution is, this is hyperbolic functions cosh lambda 1x plus c2 sine lambda 2x. And here is the example. So lambda 1 equal root square of 5, lambda 2 equal minus root square of 5. And here our solution. The second case is complex roots. So if this is the first root, the second root will be conjugate of the first root. So the sign change to minus. And the solution is y equals c1 e to the power ax cosine bx plus c2 e to the power ax sine bx. And here b and here a. And here's another example. Y double prime plus 3y prime plus 4y equals 0. Here is the characteristic equation. We use the quadratic formula. We get lambda 1 equal this value, lambda 2 equal this. So they are opposite in sign. Here is plus, here is minus. This is the first root, this is the second root. The general solution is y equal c1 e to the power minus 3 over 2x cosine root square 7 over 2x plus c2 e to the power minus 3 over 2x sine root square of 7 over 2x. The third case, when the roots are equal, lambda 1 equal lambda 2, and here is the general solution is y equals c1 e to the lambda 1x plus c2 x e to the power lambda 2x. Just this, we add x here. And this is another example. We found lambda 1 equal lambda 2 equal 2. And here our solution here. So they are the same, we just add x here. The general solution, y equal y1 plus y2. If y1 is a solution, y2 is a solution, then y1 plus y2 also a solution. To find the value of the constant, we need to solve two equations with initial conditions. So in this next videos, we will find out, we will give initial condition to find the constants C1 and C2. Thank you for watching my channel. Please, if you see my videos for the first time, subscribe and give me your likes, and see you in the next video.